Welcome to the class. We are entering into chapter 12 of the book, and we are going to be covering some aspects of material in statistics. For this class, we're going to cover sections 12.1 and 12.2. We'll start with some definitions, and then we're going to give you some tools to work with data. We take some simple examples to present the topics to you, and we'll work some of the examples step by step in a very simple way so that you grasp the idea of how to deal with data. We're learning concepts in this class. Of course, in the real world, you are going to use tools to be able to work with huge amount of data. In that case, computers are used to crunch the numbers, but we need to interpret the results. So in this class, we're going to be using some of those tools, and we develop them, like I said earlier, step by step, and have patience in doing this kind of work because it's very detailed. When working with data, a single number might introduce some error. Just one number, miscalculating a number introduces some error. Now, if you introduce a series of errors in your calculations, then your results will not be accurate. The interpretation that you get from the data will not be as good as if you were careful in manipulating every piece of data. And this is what we're going to be covering in this chapter. Some basic statistical tools that are very useful when doing calculations. Thanks. The homework for section 12.2 is listed here. Please note that no homework has been assigned for section 12.1. All right, just read the text and concentrate on solving the problems for section 12.2. It is very important that you practice the problems. And as I said earlier, pay close attention to the calculations. So we're dealing with the statistics. We have a definition here: the art of gathering, analyzing, and making inferences. Well, those are predictions that you make from numerical information obtained. There are many ways that you can obtain numerical information in statistics. You can do sampling, you can do surveys, you can collect data in a process. For example, in manufacturing, as devices are made, you can pull them at a given time, and over a period of time you calculate how many defective items are being produced so that you can correct the process and so that you can improve the outcome of the production. So numerical information is basically data, right? All the information that you collect, we call it data. And basically we have a population, right? So sometimes it's called also the universe. In this population, you take a sample, right? You basically decide to sample to see what the results are. So the sample is a subset of the population. It's impossible to collect the data from the whole universe that you have in the population. So therefore you pick up sample, and that's what you work with. So we have some definitions here. You have a random sample, selecting each item in the population with equal chance, right? So basically, everyone will have the same chance as being selected. That's random sample. No strings attached there. Then you have systematic sample. Selecting a random starting at a point and then at an nth time item or time in the population, right? So that's when you stop. Like I said earlier, in the production line, you want to know when to start, pick up all the samples, collect your data, and then stop. And by the way, always record date and time, but that's really crucial in statistics. So that when you go back and interpret the data, you have the results in front of you, and then you can write a good report. Then we have a cluster sample. An area sample frequently applied to geographic location. So you have an issue in a particular case, you concentrate on that geographic area or location, and then you get your sample from there. A stratified sample. When a population is divided into parts, it's called a strata. So this is like when you're collecting, like for example, data on children at a certain age, the elderly, working groups at a particular age, you do that. And then you have something called convenience sample. Uses data that is easily or readily obtained. Sometimes when doing calculations, like for example, you don't have the resources, you can go into your database and you can figure out, some data has been collected either by the school system, a district, a town, and then you retrieve that data and you use it to your own benefit. That's what the convenience sample is all about. In doing calculations with data, we've encountered something called frequency distribution. Frequency distribution. A listing of observed values and corresponding frequency of occurrence of each value. In other words, the frequency has to do with the number of repetitions. And we're going to do one example where this will be covered. So here we have our first example for this section on frequency distribution. And it's example number 1 on page 734 in the book. It states something like a number of children per family is recorded for 60 families that are surveyed. So you have this group of families that are surveyed, and you have a table, that this is straight from the book. And here, the idea is to count how many occurrences are taking place. It so happened that the data is so well organized right here. It's like somebody already collected the data and tabulated in a very convenient way for us to count the numbers of occurrence. For example, 0. And in the book, they just give you the number like 1, 2, 3, 4, 5, 6, 7, 8, right? They give you the number 8. But I will prefer you to start using this technique. Count up to 5. 1, 2, 3, 4, 5 will be here. So you go 1, 2, 3, 4, and then you cross. That would be your 5, and then you do 1, 2, 3. So you go 1, 2, 3. This is a very useful tool because it gives you a representation of the data instead of just writing a number. So now let's do this one here with the 1. 1, 2, 3, 4, 5. Stop right there. So it's 1, 2, 3, 4, 5. Then we go 1, 2, 3, 4, 5. Stop right there. 1, 2, 3, 4, 5. And then we get a 1. So this will be 11. We continue with the 2's, right? So we get 1, 2, 3, 4, 5. We stop right there. 1, 2, 3, 4, 5. Then we have 1, 2, 3, 4, 5. We stop right there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We stop right there. 1, 2, 3, 4, 5. And then we get 1, 2, 3. 1, 2, 3. And that's 18. For 3, we have 1, 2, 3, 4, 5. Stop right there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We stop right there. 1, 2, 3, 4, 5, and then 1. We get 11 here. And the 4. 1, 2, 3, 4, 5. We stop right there. 1, 2, 3, 4, 5. And then we have 1 left. That's equal to 6. And then the 5, we have 1, 2, 3, 4. We don't get to the 5, so it's 1, 2, 3, 4. And 6, we get 1, 2. So we only get two lines right there. And then the 7 is only 1. The 8, we have 2. 1, 2. And the 9 is only 1. As you can see from this way of drawing the numbers, here basically we don't have an idea exactly, but on the example that I introduced for you, in this case, right, you can see the picture. A picture is sort of like coming from here, even though it's not to scale. Right, this is not to scale, but you can see, right, a shape, right? A shape is emerging from the data, and that's the beauty of calculating it like this. It gives you a visual. Whereas if you just look at the number, you know, we might have an idea, but this one, it gives you really a pictorial of it. So this is what you have to do in tabulating frequencies, counting the numbers. So we move on to a subject called histograms and polygons. And we are going to use the same example that we had before with the same data, right? So let's talk about a histogram. It's a graph with observed values on its horizontal scale, right? The horizontal is right here. And the frequency on is vertical. So we have our vertical and our horizontal. Now I spent some time drawing this picture because it is important to now be able to graph what came empirically from this drawing. Basically is what is right here, but with very detailed information now. So in this case, we tabulate and make sure that you space when you draw the polygon, that the value is right at the center of each rectangle as you draw it, right? So use a ruler and also estimate for the frequencies the values as well. So in this case, when we have a 0 number of children, we have 8 here. So we have a number 8, right? So that's what this is. You draw it right there. So your first histogram start with 8. When you go to 1, you go to 11. So basically you will look for the estimate of the value of 11 is right here. So you have 8, 11. when you get 2, you got 18, so you got 18 right there. I tabulated like 5, 5, 10, 15, 20, so I more or less estimate where the value is. For 3, we have 11, which is the same as this one. For 4, we have 6, more or less around here, 6. For 5, we have 4. For 6, we have 2. For 7, we have 1. For 8, we have 2, so this is about the same height. And here is 1. So when you do in the histogram, all you have to do is, as you equidistance every point at the center, basically you have to do is draw the lines, right, and connect them. And basically, that's with the shape that you obtain when you tabulate these values. And of course, you can mark the points where they correspond, right, on the horizontal values, so that it gives you an idea where they are, right? And so this is the way you do that. Now, for the polygon, a very interesting case happens here. All you need to do for the polygon is that you go to the center of the value, right? And all you need to do for the polygon is to connect these points, right? And that's how you develop the polygon. Right, and then we don't know what's happened there, so we just put it to 0. So we go to 0 here. Right? If you use a ruler, this will really become very nice shape. But basically, that's what you need to do in these examples. These were example 4 in the book and example 5, using the data that we obtained from the distribution that we got from this example. So now let's move on. We have another technique here. It's called the stem and leaf display. This is a tool that organizes and groups the data. And this is example number 8 in the book. And so we have a table of 20 guests, right, with corresponding ages. And the stems basically means that you need to write the first number that appears on your list. Basically, in this case, is 29, so you write 2, right? And this is also organized in a nice way as well, right? So you have a 29, 31, 39, 43, and so on. So basically you have a 29 for those who are 30, 40, 50, 60, and 70. And this will be your stem, right? Now, what you put on next to it are what is called the lips, and that's where you have 20. You have 29, right? So the next one that we have for 29 that corresponds to 29 is, you look, is 27, right? Right there is 27. And then we continue in 28. So that there is no more in the 20. So that's basically all you do there. 31, you have 1, 9, and then you have a 32, which is a 2 here. Now for 40, you have a 43, 47, 44, 45. Then you have another 4 here, 44. And we continue to do this for 50. So we have 56. The next one is 59, 58, and then we get 50. We get a 0 here. For the 60, we get 60, 0, 62, and then we get 68. And for the 70, we get 71 and 72. So this will be our leaves, right? So basically that's what you need to do in this kind of example. And again, it gives you an idea as to how the numbers are behaving. You can use the same technique that I showed you earlier, right? Where you can see that the 29s has basically 3 in the family. For the 30, you have also 3. For the 4, you have 1, 2, 3, 4, 5, and so on. So this is basically what you're doing with the data. You're organizing it in this way. Now, in statistics, we always talk about percentages. This is something that you're very familiar with already, right? This is something that we know, that we have a circle. The circle in our statistical approach represent 100% of whatever is in the pool, the population. The circle represents 100%, right? And also it can represent unity. It's one piece. You haven't done anything. Everything is intact, right? The whole pie, the chart for is also called the pie chart, is 100%. And now we start to divide this into pieces, right? So if we divide the circle by half, we know that each one will be 50%, right? Each half will be 50%. Now, if we divided the circle in 4 pieces, right? If we use this, divide this in 4 pieces, then in that case we have 25%, right? Another 25% here, another 25% here, another 25% here, right? And this is something that we already know, right? This is something that we already know. But in our mind, we have to start dividing the circle into many other pieces. What if you divide it into 3 equal parts, right? So this would be like 33.33%, right? And part of the exercise is to be able to divide the pie in many other pieces, right? So in our mind, we need to start to think if you divide this in 8 pieces, right? So if you were to divide now the circle in 8 pieces, what do you get, right? So if you were to divide it like this, right? In that case, every piece, right, will be 12.5%, 12.5%, and so forth, right? So if you could subdivide in this square here into little pieces, then we have to start to think into 5%, 7%, 12%. But this gives you an idea how that division will take place, how you will be subdividing the circle. But remember, the whole thing adds up to 100%, right? And this one, it will give you an approximation here. And so this is what you need to start to think in terms of statistics think about percentages. Later on, we're going to be talking about the normal curve, and this basically is useful, but at the same time, we'll have to memorize certain percentages, because here is very nicely divided and you get a nice calculation. Whereas as you will see later on, when we do the normal curve, you have to memorize some percentages. You cannot really see it as straightforward as a picture. We are moving on to example number 9 in the book, found on page 742. And in this example, we are given a pie chart with certain percentages. We have tigers, 38%, elephants, 26%, acrobats, 17%, jugglers, 14%, and then there are other performances of 5%. And the issue is that they want to calculate the preference of the people in this circus performance. There are 800 people that are participating in this study, and we can see the percentages right here. And now to calculate how many people, like the tigers for example, we need to do the following calculation. We know it's 38%, we turn it into a decimal, right? Remember, to turn a number into a decimal, basically you divide it by 100, and that will give you the decimal form. This is the decimal form that you will use to calculate how many people. So in this example, we have a 0.38 times 800, 304 people liked the tigers. The elephants, we have a 26%. The decimal point is 0.26. We multiply by 800, we get 208 people that like that performance. The jugglers, 14%. Sorry, the acrobats is 17%, is 0.7 times 800, 136 people for the acrobats. Juggler is 14%, 0.14 times 800 will give you 112 people, and 5% of the others functions in the performance, 0.05 times 800 give you 40. In total, you get 800. Remember, it's always good to double check your work. As I said earlier, we need to pay special attention to the calculations, because if we make an error in our calculation, it will be displayed in the outcome. So we'll get the wrong information when we're doing this type of calculators. This type of calculations are important. So my suggestion to you is to pay attention to the numbers when you're calculating. If you want to use this form, it's fine. You can use a calculator, or you can move the point. Remember, you can always move the decimal point 1, 2, right? That's divided by 100. You move the decimal point 2 places, and that's that. Anyway, this is what you need to do in terms of this work, and